was the greatest engineering marvel of the 20th century, forged from the brutal cold and unforgiving winds. Can humanity conquer nature to build a structure that changes the course of energy history? Today, we're diving into the story of the Trans-Alaska Pipeline System, a monumental battle between humanity and a treacherous landscape filled with unimaginable challenges. Picture this: it's the early 1970s, and the United States is in the grip of an energy crisis. The nation's thirst for oil is growing, but supplies are dwindling. Then, a glimmer of hope emerges from the frozen north. Vast oil reserves discovered in Prudhoe Bay, Alaska. But there's a catch. How do you transport millions of barrels of oil across 800 miles of some of the most inhospitable terrain on Earth? Enter the Trans-Alaska Pipeline System, or TAPS, a feat of engineering so ambitious it would push the boundaries of human ingenuity and determination. This wasn't just about building a pipeline. It was about taming a wilderness that had resisted human intervention for millennia. The historical context of TAPS is as fascinating as the project itself. In 1968, when oil was discovered in Prudhoe Bay, the world was changing rapidly. The Cold War was at its height, and energy security was becoming a critical concern for nations worldwide. The United States, in particular, was looking to reduce its dependence on foreign oil. Alaska, with its newly discovered riches, seemed like the answer, if only they could find a way to get the oil out. The significance of TAPS cannot be overstated. It wasn't just about oil. It was about proving that humans could overcome seemingly insurmountable obstacles. The pipeline would traverse 3 mountain ranges, cross over 800 rivers and streams, and cut through terrain that had never seen industrial development. It would need to withstand temperatures ranging from -80 degrees Fahrenheit to 95 degrees Fahrenheit, powerful earthquakes, and the constant threat of corrosion and fatigue. But perhaps the most formidable challenge was the permafrost. This permanently frozen ground covers much of Alaska, and it presented a unique problem. If the hot oil flowing through the pipeline were to melt the permafrost, it could cause the ground to shift and potentially rupture the pipe. Engineers had to devise a way to keep the permafrost frozen while allowing the oil to flow freely. The harsh climate of Alaska added another layer of complexity. Blizzards, ice storms, and winds strong enough to knock over heavy machinery were common occurrences. Workers had to contend with these conditions while handling delicate equipment and performing precise tasks. It was a test of both technology and human endurance. Earthquakes posed another significant threat. Alaska is one of the most seismically active regions in the world, with frequent tremors and the potential for devastating quakes. The pipeline would need to be flexible enough to move with the earth, yet strong enough to maintain its integrity under extreme stress. Crossing the varied terrain of Alaska was a logistical nightmare. From the North Slope's tundra to the Yukon River's floodplains, from the Brooks Range's peaks to the taiga forests of the interior, each section of the pipeline required unique solutions. Bridges, tunnels, and elevated sections had to be constructed to navigate these diverse landscapes. The sheer scale of the project was staggering. At its peak, over 70,000 people were involved in the construction. The pipeline itself would use more than 500,000 tons of steel, enough to build nearly 50 Eiffel Towers. It would pump up to 2 million barrels of oil per day across the state, covering a distance equivalent to that between Los Angeles and Chicago. To overcome these challenges, engineers had to think outside the box. They developed innovative solutions that would set new standards in pipeline construction. For the permafrost problem, they designed a unique above-ground pipeline system. More than half of the pipeline's length was elevated on vertical support members equipped with heat pipes. These pipes would conduct heat away from the ground, keeping the permafrost frozen. To deal with earthquakes, the pipeline was built in a zigzag pattern, allowing it to flex and move with the earth. Special sliding supports were used to allow sections of the pipe to move independently. For river crossings, they developed techniques to bury the pipe deep beneath the river bed, protecting it from ice and flood damage. The impact of TAPS on Alaska and the United States has been profound. It transformed Alaska's economy, bringing jobs, infrastructure, and revenue to the state. For the U.S., it provided a crucial domestic source of oil, enhancing energy security during turbulent times. The pipeline has delivered over 17 billion barrels of oil since it began operation in 1977, playing a vital role in America's energy landscape. But TAPS's legacy extends beyond oil. It pushed the boundaries of engineering and environmental management. The project led to advancements in cold region construction techniques, wildlife protection measures, and pipeline safety technologies. It demonstrated that large-scale industrial projects could coexist with fragile ecosystems when proper precautions are taken. The Trans-Alaska Pipeline System stands as a testament to human ingenuity and perseverance. It shows that with determination, innovation, and respect for the environment, we can achieve what once seemed impossible. From the frozen tundra of the North Slope to the port of Valdez, TAPS continues to be a lifeline of energy, a marvel of engineering, and a symbol of human achievement in the face of nature's greatest challenges. The Trans-Alaska Pipeline Project is a testament to how human innovation and perseverance can create extraordinary achievements. Thank you for following this inspiring journey. If you found this video helpful, be sure to like, follow, and subscribe to the channel so you don't miss out on the best content about science, technology, and history. See you in the next video.